joining in for the talk today. So I'll be this is the work that I've been been doing for my PhD. This my thesis advisor, my PhD thesis advisor is Mark Rast, and this work has been done in collaboration with Basilio Ruiz-Cobo from ISC Tenerife. Basilio is also the author of this SIR inversion code. Okay, so in this talk, I'll try to keep things simple. I'll only be talking in terms of single variable inversion, and specifically talking only about inverting temperature in the photosphere. So the first things first, what exactly are the inversion problems? So when we look at the sun, or you have basically, so there are basically two things in the system. One is the solar atmosphere, the model, like the temperature or the pressure, the magnetic fields that define the solar atmosphere. And then you have the spectra that come out of this solar atmosphere. So there are two pieces in the problem. The first one is called the Fourier problem. So which is basically defined as given a solar atmosphere, like temperature or the gas pressure, what is the Fourier problem solves for the emergent spectra coming out of the solar atmosphere. So on top of that, when you're solving and the inversion problem basically is that when you're given a solar spectra by this, the inversion problem basically takes you from the and asks to infer for the atmosphere that would have actually resulted into the spectra. So the basic idea with inversion is that you cannot directly get or compute or you cannot directly measure the solar atmosphere, so you rely on indirect method to actually infer for this solar atmosphere from using the solar spectra. So again, in summary, the question basically is to find the temperature profile that resulted into the observed spectra. So next question basically is that how exactly the inversion is done, the basic concept. So in here, what I'm plotting is the temperature on the y-axis, and on the x-axis is the depth. In the red curve is a starting guess model. I'll explain what exactly that means. And in the black, but that you can barely see, is the actual is the observed atmosphere that you're trying to invert for. So everything in here is artificial. I just like made it added. So everything here, there's no observations as such. Everything is artificial here. And then the green curve basically is the difference between the black and the red curve, which is the delta t, and which is the unknown. On top of that, what you also have is the spectra coming out of all these things. So the red one, so the red curve corresponds to the spectra, the synthetic spectra coming from the guess model. The red curve, the black corresponds to the observed spectra coming from the observed model, and the green is the difference between these two models, the observed and the guess model, basically. So in inversion, basically delta t is unknown. That's what you're solving for. And the delta I is known. So in summary, the question it boils down to is that what delta t that you need to add to this red curve to the guess model, such that your resulting the final delta t, delta I, actually goes to 0. So that's basically it. So you start with the guess model, assuming that it's close to the real atmosphere, and then you ask for like what changes do I need to add to this guess model so that my resulting spectra matches the observed one. So then for that, you actually need to find a connection between the spectra and the model. And for that comes in the response functions. The response functions are basically defined as, so the response function depend on two things, the wavelength and the depth of the model. So it's basically defined as like, if I make a small change in temperature at a given depth, how much my intensity for a given wavelength changes. So in some sense, it also is measuring the sensitivity of my spectra to the model at a given depth. So if my spectra does not change if I change my temperature at a given depth, that just means that the spectra is non-sensitive to the temperature at that depth. This is clearer in the plot here. So in the bottom left plot, what I'm plotting is the response function on the y-axis, and the x-axis is the depth, and the right side is the spectra versus the wavelength. So here, so what I'm showing here is the green is the response function corresponding to the line core wavelength. So what it's saying that my line core is actually more sensitive to shallower regions, whereas my the continuum wavelengths are basically sensitive to deeper regions. Uh, so this is the response function for just two wavelengths. So if you plot for all the wavelengths, this is what the response functions for all different wavelengths as a function of depth look like. Okay, so in inversion problem, what basically are you actually? Everything basically boils down to solving a linear system of equations based that is the ax equals b. So let me just like follow this thing. Yeah, you through. So again, this is the response function in differential form, which is equal to delta I over delta t. So you can convert this in the integral form, which can also be said that your net delta I, which is the difference between for a given wavelength, which is equal to the net change between the real and the guess atmosphere, weighted by the sensitivity at that depth. So you can this integral form, you can write this in a vector equation. The response function vector times the delta t vector equals your delta I, the total delta I. And for if you stack multiple wavelengths on top of each other, this will actually lead to a matrix equation, which is your ax equals b that you're solving. So in inversion problem, it's always talked about like why exactly that. It's always talked about that inversion problems are highly non-trivial. And so here I'll be talking a little bit about why exactly it's highly non-trivial to solve for delta t in this ax equals b equation. So you would be thinking this is like a simple linear system of equations. Why not just find the inverse of the response function matrix, multiply on both sides, and you just get an identity of here, and then response function inverse time delta I will give you the delta t. It's just like your system. So in here, the complexity is basically coming in is that your system belongs to something that is called as a discrete ill-post problem. In very simple terms, it just means that your response function is highly inconditioned. That means that your singular values are super small. So on the right in the plot here, what I'm in the plot, I'm showing is the singular values of the response function matrix. So if you do the SVD and spit out the singular values, this is how it's going to be distributed. In here, I'm only plotting 25 singular values. In my system, I have about like 120 singular values, and you can see that these singular values are like super small. So the reason why singular values are important is that when you compute the inverse of the response function, these singular values are the one that actually go in the denominator, and that what that eventually leads to is that the inverse or the pseudo inverse in this case, because the inverse of response function does not exist, will have really high large amplitude. So what that corresponds to that if you have any error in your system, this large terms in the response function inverse matrix will actually these large terms will amplify amplify the error. So in the bottom right, what I'm plotting is the delta t versus the depth. So what this means is, so the green curve is basically how far my guess model is from the real atmosphere. So if you had, and in the red I'm computing is like how far my inverted atmosphere is away from the observed one. So if my inversion were perfect, you would expect to see a flat line because then your inverted t will match the observed t. But what you see is like because of this large amplitude terms in the inverse matrix, the error has been amplified, and that leads to your inversion solution that is like totally far away from the zero line. So given that your response function is highly ill-conditioned, it's by itself is not an issue. The issue basically comes in is because you have error in your system. There are basically three sources of error in your system. One is that can actually corrupt your three sources of error in your system. The first one is when you have other variables like pressure. We are not talking about that, so it boils down to two errors. The first one is basically the error source is this noise in the spectra. The second term that actually acts as an error in the system is the higher order terms that you have missed out. So this response function is basically a definition in terms of like it's actually an approximation. It's the first order approximation. Sorry. So what you can do, you can see your delta I as a Taylor series expansion in delta t. and response function is just basically response to the first order term here. And but on top of that, you also have these higher order terms in the system that you have missed out when you're computing the response function inverse of the matrix. So given the fact that you have so sorry, in this talk, I'm also not going to be talking, won't talk about the spectral noise, but it will be similarly dealt with the higher order error terms. Okay, so so combine two things. First, that you have these error terms in the system, and that you have your response function is highly ill-conditioned. What that will actually lead to is error amplification, which will further lead to your inverted solution is dominated by error, and the solution are like going to be highly oscillatory. So okay, so this again in this plot, you have the delta t on the y-axis, and the x-axis is your depth. If you did not have any error in your system, no matter how you compute your pseudo inverse of the matrix, you will because there are no errors, there is no error amplification, and you can perfectly solve your system basically, which is depicted by this blue line. But the moment you add error into your system, those error will be amplified, and your solution will be dominated by those errors. So so how do you exactly deal with the error is then you regularize your system to get a sensible or a smooth solution, or in simple terms, get a non-oscillatory solution. So regularization, just in a very simple term, means that you are better conditioning the matrix, or you're solving a system which is better conditioned, basically. And again, on the right side, I'm plotting the singular values. And sorry, one of the points that I missed in is that your system has there's only like 11 eigenmodes that actually corresponds to most of the information content in your system. Okay, sorry, jumping here a little bit. So in regularization, the basic idea is like when you're computing the inverse of the matrix, you remove these singular values that are super small in amplitude. What that eventually will lead to that your response function has smaller amplitudes, that just further will lead to lesser error amplification. This is how it's exactly done in the R-less inversion method. This is one of the inversion methods that's used in helioseismology. R-less stands for regularized least square methods. In this, you solve for delta t at all depths, and you regularize the system by removing the small singular values. And when you do so, so in here, in the plot, I'm keeping 5 eigenmodes, and then my inversion solution corresponds to the blue one. Please don't worry about what is why the shape of this blue curve is like super weird. The intention is that blue curve should be closer to the 0. It is compared to the green one, but the moment the moment you actually in this you add a few more eigenmodes that actually lead to so the blue curve was constructed using only 5 eigenmodes. Then you if you add a few more eigenmodes to the system, say 8, your error will be amplified, and your solution will be corresponding to will be a highly error amplified solution, basically. So okay, so there's another way of regularizing obtaining a smooth solution, which is the nodes way, using the nodes. In the left, I'm plotting the temperature versus depth. On the right, the spectra versus the wavelength. In this, what you do is like you define a few depth locations, depicted by these blue dots, and you only compute the delta t, or you solve for delta t only at these blue dots, and then you find the rest of the delta t at rest of the depth by interpolation. This forcingly ensures that your solution is not oscillatory, and you obtain a smooth solution. Okay, so one of the hardest problems, or the most of the issue that boils down in inversion, is basically finding the right regularization parameter, or how to actually regularize your system. Okay, so I just want you to like keep that in mind, that in inversion, everything just usually mostly boils down to how to regularize your system. Okay, and so the inversion methods and a few in the inversion methods that I've talked so far in the R-less and node base, they focus on they focus on inverting for all variables at all depth locations at the same time. So the basic tagline that I think is associated with them is that is to find an overall smooth atmosphere that best fits the observed spectra. Okay. Now talking about the OLA inversion method and how. Okay. So, and the tagline with the OLA inversion method on contrary is that it actually focuses on trying to invert for one variable at one depth location at a time, while minimizing the crosstalk from all the other variables in the system if they are present. Okay. So OLA stands for optimally localized averages. The method actually originated in geoseismology in the late 60s by Backus and Gilbert, and was then later adopted by helioseismologists to invert for the internal structure of the sun. And now I am just further extending the method to apply it to solar spectropolarimetry to invert for the solar atmosphere in the solar photospheric atmosphere. Okay, so OLA stands for optimally localized averages. In the plots here, I'm plotting the response function as a function of depth for all the wavelengths. On the right side, you have the response function in the background, and then on top of that, you have this red curve, which is something that is called as the averaging kernel. Okay, so the basic intention in OLA is to linearly combine these response functions so that your net sensitivity is highly localized at one depth location and it's small everywhere else, basically. So indirectly, what you're trying to do is like you're trying to improve the capability of your probe to do inversions. So yeah. Okay, so so next question comes like, how do you exactly go about computing the averaging kernels? So it's basically so what you do is like you actually solve the linear set of equations. So you give the system you prescribe something that's called the Gaussian target function, and you ask the system to solve for these coefficients, these linear coefficients that will take your response function and make it resemble or make it close to the target function. So so again, these coefficients are the linear are the numbers with which you are actually linearly combining your response functions with. Okay, again, then the question again, sorry. So again, you're back to the linear system equations. You're solving the linear system equations for coefficients so that your response functions become the target function. And the way, again, logical ways to find the response function inverse that you can multiply on the both sides to get the coefficients. So in the OLA, the basic intention also is that you should also keep only a few eigenmodes while computing the response function. It will become clearer why in a few slides. Okay, the more eigenmodes. So on the top right, I'm plotting the eigenmodes that you're actually. So the eigenmodes in the depth direction. So when you take the SVD of the response function matrix, it gives you the eigenmodes in the depth direction. And I'm plotting the first 5 eigenmodes and how they look like. And in the bottom, what I'm showing is that as you keep more of these eigenmodes to compute the inverse, the closer your average kernel gets to the target function, basically. So in here, if I keep like 15 eigenmodes, my average kernel, the red curve, corresponds to the blue curve, basically. But at the same time, what it also leads to is that it leads to the coefficients actually being larger. So why having a large coefficient is an issue is basically that these coefficients actually then later get multiplied to the error terms, and then that leads to the error amplification. So that just means that you cannot keep like all the 120 eigenmodes, because if you do that, your coefficient will practically go to infinity, and that means just your error will go to infinity. So, okay. So next step basically is like, how does exactly finding the coefficients lead to an inversion? So starting with the first order approximation equation, you multiply by the coefficient that you have just computed, just opening up the equations. So this is basically my averaging kernel. And that averaging kernel then acts on the underlying delta t, leads to my average delta t at that location. Okay. This is clearer from the plot. Okay. Let me explain. Okay, in the background, the green curve corresponds to my delta T perturbation that I have that I'm trying to invert for. This is the difference between the real atmosphere and the guess atmosphere. The red is the averaging kernel, and the blue is the target function. Okay, so in OLA, once you have found these coefficients and constructed your averaging kernel, the inversion at this depth basically corresponds to this green dot, which actually equals to this red curve multiplied by this underlying green curve. So, and on the right hand side, and okay, so sorry, and like please interrupt like if something is like not making sense at all. Okay, so in OLA you have computed these coefficients and finally constructed these averaging kernels. And again, I should emphasize that you do inversion at one depth location at a time. So once you have constructed the averaging kernel at this depth, the inversion delta T corresponds to this red curve multiplied by this green curve and added up in the tau location. And your inversion actually corresponds to the right hand side because you have the delta I and you have the coefficients. Yeah. Okay, so one of the key takeaways from here is like if you can construct narrower averaging kernels, you're doing lesser averaging, which implies that the delta T that you have computed will actually get closer and closer to the true delta T at that depth. So but then the caveat at that point is like as you're keeping more as you're constructing narrow averaging kernel, your errors are also going to get amplified, so you have to be careful about that. Okay, so this is a plot that I took from the last slide. So you have done inversion, which is the green dot at one depth location. Now that next question that comes in is like, how do you actually do inversion at all depths? So how you do it is basically that you slide your target function from one depth to the other. So you pick one depth location, try to compute the average kernel at that depth location, get the coefficients, multiply coefficients by delta I, compute the inversion, then you move on to the next one, and you keep sliding it from from the deeper to the shallower ones, basically. And so in here, the green dots basically corresponds to the the inverted delta T at each of those steps. One of the key points that I want to mention is basically in the shallower ones, you can only construct a wider averaging kernels, versus in the deep ones, you can construct narrow averaging kernels. This is due to the fact that in deeper locations, you have more orthogonal information so that you can add and subtract to construct narrow averaging kernels, while in the shallower one, you have like only very small number of orthogonal information, so that prevents you from actually constructing narrower kernels. Okay, so there are like some really important strengths of the OLA method. So this this plot is taken from the last slide. On top of that, what I've plotted here is this black curve, which corresponds to the width of this averaging kernel that you have constructed. So what it's trying to tell you that in the deeper regions, the width of the averaging kernel is super small. That just means that you're doing really good inversion, really localized inversion at those locations. Whereas in the shallower ones, so this is like me re-emphasizing the point. In the shallower ones, you can only do like wider, or like you can only do like wide, heavily averaged inversions, basically. On top of this, the OLA method, given that you have the width of these averaging kernel, you actually know what your inversion corresponds to. You know how much averaging that you have done in the vertical depth domain to compute this inversion delta T at that depth. Okay, what OLA method can also allows you to do is like it also allows you to quantitatively assess the quality of your inversion. It also allows you to assess the capability of your lines to do the inversion. So if you are given a given set of lines, you can tell that the capability of lines and the inversion are then basically the assessment of the capability of the lines are based on how localized of the averaging kernels that you can construct, and what is the domain in which you can actually do inversion, and if you have crosstalk, how much of the crosstalk you can actually minimize. You can use this information in reverse and actually ask the question like what line combination could actually lead to the most localized inversion, or like specifically the question is like if you are given the 10 line sets and you can only observe like 5 line sets, this method can actually quantitatively tell you like this 5 line set combination can actually lead to the best inversion based on these criteria. And using this, I do have an intention to develop a toolkit for DKIS. Sorry, I'm like selling this a little bit, sorry, but that can actually potentially find the best line sets quantitatively for a given scientific problem. And the best part about this this toolkit will be that this can be actually used irrespective of the choice of the inversion. You can use whatever inversion code one can use whatever inversion code they want to, but this can actually help them assess what lines or where should they actually be observing. Again, a lot of assumptions are going into making this assessment, but like as just a starting point, you can compare one line versus the other and tell them if whether one is better, what line combination is better versus the other or not to do inversions at a given depth. Okay. Okay, so I'm going to talk a little bit about like how it's just this slide about like how it's actually done in conventional OLA method. So in conventional in helioseismology, there's a very so conventional OLA in helioseismology basically assumes a strict linear regime. Like that means that when you're solving this linear system of equations, your delta t that you need to compute is very small. That means that your guess model is like super close to the real atmosphere, which further means that you do not have to do any iteration. You just compute the response, the inverse of the response function once, you multiply on both sides, and you get your delta t, and you're good to go. And that's it. You don't have to update your guess model, and then you have to feed that new guess model to the system and iteratively solve for delta t. But in the reality, when you do spectropolarimetric inversions, your delta t is usually large. And how? Okay, yeah. And so starting from the first order, first order approximation, this adding the higher order terms to complete the equation. When you compute, once you have computed the coefficients and you slap them in. Okay, so when the delta t is large, that just usually means that the higher order terms are large. For a given coefficient, that will mean that you will have larger amplification of error if your delta t is basically large. Okay, so this is gonna be clear, like why. Sorry. Okay, so your intention basically is to construct super narrow averaging kernels so that your inverted delta t is close to your true delta t at each depth. Okay, if your delta t is large, okay, let me explain what this plot is. So on the left, I'm plotting the delta t, which is similar to the old delta t plots, delta t versus depth. The red one corresponds to how much my guess model is away from the real atmosphere. The green corresponds to the inversion after one cycle, basically. And on the right side corresponds to how the plots look in the actual temperature. You have the red one, which is your starting guess model, the black one, which is the real atmosphere, which is what you're trying to invert for, and the green corresponds to the inverted delta t. Okay, so if your delta t is large and you are keeping only a few eigenmodes so that you're trying not to amplify the higher order error terms, you can only do you cannot actually do a really good inversion. That means that this green curve will not be close to the black one. But on top of that, if your delta t is large, and if you keep too many eigenmodes so that you can construct narrower averaging kernels, the solution will actually be amplified by the error terms. Yeah. So you are like in this dilemma whether you should be keeping too less of an eigenmode so that your error is not amplified, or you should keep too many eigenmodes so that you can do better inversion, but at the same time the inversion solution is actually dominated by the error. Yeah. So the key takeaway from this slide is that the amplitude of the higher order term and all the other sources, if you have any error in your system, that will actually dictate how many eigenmodes you can keep. And how many eigenmodes you can keep actually dictates how narrow of these averaging kernels that you can construct, and also the resolution of, or like how well of inversion you can actually do. Okay, so this, to get away from that, when you have larger delta T perturbation in your system, there's a workaround, which is the iterative OLA. And in iterative OLA, the basic scheme is that in the starting cycles, you try to play safe. You keep only small number of eigenmodes and invert with like super wide average kernels. So when you keep smaller number of eigenmodes, your coefficients are super small. That just means that your error, the error terms are not going to be amplified. And as you go in further cycles, and as your delta I, as your inverted atmosphere gets closer and closer to your real atmosphere, your delta I gets smaller. And when that happens, your higher order terms are actually going to be smaller. And in that case, you can actually take more risks. You can actually keep more eigenmodes so that you can construct narrow averaging kernels. That means you're doing a higher resolution inversion, basically. So in summary, in starting cycles, you do smooth and low resolution inversion. In later cycles, as your delta I goes down, you do a high resolution inversion. When you incorporate this scheme, so this is when you incorporate this iterative OLA scheme. This is what the results look like. So again, the red one is you're starting how much you get starting guess models away from the real atmosphere. The green one is the OLA iterative OLA inverted atmosphere, and in the blue, for comparison purpose, I'm plotting the SIR inversion, what the SIR will spit out. And again, the idea is like you want these curves to be close to zero, and in which case your inverted solution, and if they're close to zero, your solution would be closer to the real atmosphere. Okay, yeah. And again, if Basilio were like doing inversion, he would have done like way better inversion with SIR. But I'm just like putting that like as if you use the standard parameters for the SIR, this is what the inversion actually comes out to be. Okay, so in here I have put in like Gaussian shift perturbation. There's another case that I've like tried to test this iterative OLA. The method on is like I have two Gaussian shape perturbation which are of the same sign. This is particularly hard because oscillations have positives and negative. So this is a particularly hard case to solve for, and SIR kind of like struggles to invert for this perturbation. And the green curve, because it's also struggling in this region because you don't have a lot of information there, and you cannot construct like super narrow averaging kernels in those locations. But in deeper ones, the OLA inversion is doing pretty good, and your system, the inverted solution is super close to the real atmosphere. And again, like all of these solutions are basically when you do not have any noise in the system, and the spectral noise in the system. Once you add spectral noise, the limit will change. It will actually further constrain how many eigenmodes you can actually keep, basically. Okay, so one of the key places where OLA struggles is actually inverting for large-scale perturbations. What do I mean by that is that, and if I talk about the most simplistic case that you can put in, most simplistic perturbation that you can put in system is constant delta T. So in here, I have put in a 500 Kelvin constant delta T perturbation system and try to invert for it. And the OLA really struggles to do inversion, to invert for this constant one. And then, but SIR does a really, really good job. The SIR is like flat right here. SIR does a really good job at inverting for this constant perturbation, because by construct, it tries to invert for constant perturbations in the system. On top of that is you have another case. If I talk about another case, you have a constant 500 Kelvin perturbation, but on top of that, I'm also putting another Gaussian perturbation on top of that. In that case, both SIR and OLA struggle to invert for the real atmosphere. Okay, so we did figure out why exactly that was happening, why large-scale perturbations were harder, and we can talk about that if someone is interested in why that is the case. So what we eventually, but to solve for like this large-scale perturbation, what we eventually figured out was that uh, we actually got down to this constant OLA inversion. This is in which the idea is to compute for the large-scale average in the OLA framework. Okay, the way you compute average delta t is basically like if you just like look at the mathematics, like average delta t over all the depth is basically going to be you sum over the delta t's at all depth and divide by the number of depth points. So if you can construct averaging kernels which are flat, that way you have these two are basically equivalent in that case. So in this framework, what we are in this constant OLA inversion framework, what we are trying to do is we are basically trying to not construct a localized Gaussian averaging kernel, but we are trying to construct a flat averaging kernel which has the amplitude of 1 over number of depth points. And the way we are incorporating this is now is like on top of doing this highly localized, high resolution inversion using the Gaussian averaging kernels, you put in this constant OLA inversion on top of this. So you do normal OLA inversion, which is the Gaussian one, and then you do the constant OLA inversion. Then you do again, you take the results from both of them, put in like, and then you iteratively solve for delta t. So what that actually leads to is basically the basic idea then is like you interleave constant OLA inversion in between the normal OLA inversion to do large scale and high resolution inversion simultaneously. When you apply this scheme, so these are the plots from the previous slides, how the inversion for large scale perturbations look like when you have not added this constant OLA inversion. But the moment you add this large scale, when you correct for this large scale perturbation in the OLA framework, they do a pretty good. The OLA does a pretty good job in most locations, but like the regions where you do not have a lot of information, it does not. It's still not able to fix that. And again, in the second case, basically the constant plus Gaussian, this before large scale perturbation correction. After you correct for large scale, perturbations, the OLA is doing a pretty good job in the deeper regions where it can also form like narrow averaging kernels, but SIR definitely struggles to do the inversion. One of the other cases I'm just like putting this here is like a cosine shaped perturbation. This is just like me getting like a little bit exotic regime or something. So you have a cosine shaped this red curve, the cosine shaped perturbation into your system. Again, the OLA does a good enough job in the deeper regions, struggles in the shallower ones, while SIR struggles to invert for this cosine shaped perturbation. So a little bit about like what are the advantages of the OLA method is so in OLA basically the basic advantage is that the user has a lot more control over what their inversion corresponds to. You can control the width of this averaging kernel, and that will change. So yeah, you have more control about the shape and the width of this averaging kernel. And then also that you also know what your inverted delta t corresponds to in terms of like how much averaging that you're doing to compute this inverted delta t. Again, then the limit to the vertical resolution is then further is the limit to the vertical resolution is determined by the response function, which basically depend on the guess model and the spectral line sets. Then also depends on the higher all the error terms in your system and also the crosstalk from the other variables. The OLA, what can also be used is to assess the capability of different line combinations to do the inversion. That's another advantage. And given that OLA inverts for one variable at a time, what it can do is like it can help minimize the crosstalk from other variables, and this could further and this concept that it can actually be used to actually help us to invert for electronic pressure or gas pressure in the presence of temperature, which is a really hard thing to do in spectropolarimetric polarimetric inversions. So I think I went really, really fast, I guess. With that, I will take questions. Yep. Thank you.
Okay, thanks, Piyush. Does anyone have any questions? So I have a question on how does this compare to node-based inversion in terms of speed?
So in so yeah so there is node-based inversion basically.
Yeah, I mean, but how quick is this one compared to SIR?
Oh, we have not worked to speed up the inversion. I think like SIR takes about like a few seconds to do the inversion. This will take like a few tenths of seconds to do inversions, basically. But yeah, we have our intention has been to just like to get the proof of concept that the method actually works to do inversions, and then later we'll actually work on the speed and everything.
But there's nothing inherently slower about this than the node-based version. Well, once you optimize this, there's no reason to think it should be either quicker or slower than SIR or anything equivalent.
Sorry, I think you're cutting out. I am not able to. Sorry.
I just wonder if there's any inherent reason behind this OLA method that would make it faster or slower than SIR or any other node-based inversion scheme.
I think it will inherently be slower than SIR because
Okay.
you're doing one variable, one depth location at a time, and you're iterating over multiple depths, and then multiple variables at the same time. And whereas SIR is basically computing at all depths, all variables at the same time, and then iterating it. So it should be inherently slower than SIR because of that. Yeah.
Okay, thanks. You have a question, Han?
Yes. So Piyush, this is Han. When you calculate your averaging kernels, you need the response function, right? A response function at all wavelength. So do you update after each iteration those response functions, or do you keep the response functions from your initial gas atmosphere?
So for one, as you're iterating to the individual depths, the response function is kept the same. But once you updated your model, I update the response function.
Yes. Okay.
Yeah.
And the second question. So in principle, you could do something like for a node-based solution, you could do something like stick and use more nodes and then regularize, for instance, for short spatial scale variations. Have you tested that?
I have not. So I think that is getting closer to the RLS method where you actually
Yes.
invert for all depth location. You just remove the nodes and you just like regularize just by keeping only a few eigenmodes. I mean, like, yeah, yeah. So the reason where I think I have not tried. I'm like, again, I've done RLS inversion and they're good. I think the reason OLA is different from RLS because you have control over these averaging kernels. In RLS, because you're solving for all depth locations and all variables at the same time, you do not have any control. You can plot those averaging kernels, but you do not have a control over like how much wide of these averaging kernels you can actually construct.
Yeah.
Whereas in OLA, yeah, go ahead. Sorry.
No. That's. I mean, think one could certainly conceive something like a combination of a SIR-like and an OLA based inversion, where initially the first few steps you do a node based, and then to the refinement you do a OLA based.
I thought about that. I think the reason, and again, I've not thought it through all the way, and I think the reason, the caveat of not doing this. This piece was basically, I thought of first doing this in the SIR framework. I think this is exactly what you're talking about, like to do the large scale perturbation or large scale inversion using SIR and then do the refinement using the OLA. The reason, sorry.
No, I was just talking about speed, not necessarily.
Okay. Yeah, okay. So I think using SIR to do, yeah, okay. If it's just about speed, then yeah, okay, I get it. Okay, fine.
Okay, thanks.
Any other questions? Okay, if not, then thank you, Piyush, and thanks everyone for coming.
Cool. Thanks, Paul.
Yeah.
Thanks so much.
Thanks, very nice, Piyush.
Thanks, Tom.